Welcome to Hot Chips 33. Session 4, Enabling Technologies.
Our first speaker today is going to talk about heterogeneous computing to enable the highest levels of safety. He is Ramanujan Venkatadri from Infineon. He's a principal engineer in the Silicon Valley Innovation Center at Infineon Technologies based in the Bay Area. He's been with Infineon since May of 2018, focused on strategy, technology innovation, and software system security and functional safety. He has a decade's experience in developing and architecting real-time safety-critical embedded software for various automotive ECUs, and he's worked at many automotive companies in Europe, Japan, and India. Let's welcome Ram.
Thanks, Rob. Thanks for the introduction. Hello, everyone. I'm Ramanujan Venkatadri from Infineon Technologies. Today, I will be discussing a few of the key challenges of next-generation automotive systems and how we at Infineon are trying to solve them. First, quick look at the table of contents. I'll be discussing over the challenges of the next generation automotive embedded systems, and we'll go a little detail to understand each of the challenges, and then a quick look at the Infineon components or Infineon chipsets, how these solve the next generation challenges typically. And at the end, we'll also have a quick look at one of the application use case, how the Infineon microcontroller can be used in a device. To meet the next generation automotive systems, for example, to achieve autonomous electric and connected vehicle goal. So it's very challenging because there are a lot of hops you need to understand, and also you need a lot of different compute systems, connectivity, and various aspects. Here I'm comparing it to climbing Mount Everest. It's not impossible, but it's difficult to attain. So how we could achieve the connected electric and autonomous future with the existing technologies today? At the base camp, we have evolving technologies like battery, sensing, and AI. For example, AI is one of the phenomenal technologies being used in self-driving, also predictive maintenance, state of health, and state of charge estimations in battery technologies today. With that, we have to achieve connected and autonomous electric mobility's future. So what are the challenges on the journey? First, we need to have workload-specific compute capabilities with some accelerators to support specific tasks. For example, machine learning, sensor processing, etc. Next, the devices will be connected to an external world. How do we support extensive security features to enable it to communicate to the external world? Third aspect is availability overall with the functional safety aspects, how the device will be available at all times, at all duration, to make sure that it is safe for passengers to travel. And next, to adapt these kind of changes, how can the EE architecture need to be evolved, and also it need to be adaptable to enable new features and new challenges immediately, and also without having much of legacy impact over the vehicle architecture. Let's look at the specific aspect of the workload, how exponentially the workload has been increasing in the automotive. Primarily, the first aspect is the deep learning aspect or machine learning aspect, where machine learning is used in various aspects or use cases in automotive today. For example, for predictive maintenance, state of health, and state of charge estimations in battery management systems, and also for object classification, object detection, and also for environmental predicting. And with respect to the sensors specifically, we should be also able to have specific accelerators to process them faster and leaner so that you can have the data for application use cases. Next, you should also have faster security accelerators to enable faster authenticity, integration, and also secure communication across the vehicle and outside the vehicle. Next is to support the EE architecture evolution. You should have higher connectivity for zonal or EE zonal architectures and also domain architectures. And you should also have low latency data processing to support data movement across the vehicle. Coming to the connectivity, any point which communicates to the external world is a point of threat. It could be logical attacks, side channel attacks, spoofing, repudiation, various kind of attacks which could hamper the vehicle security. So you need security at every potential entry point in the car. And coming to the functional safety aspects, today what you see in the systems are fail-safe systems. In case of a failure, it enters the safe mode. For example, for electric power steering system, if you're driving and if it fails due to some functional fault within the ECU, it enters a fail-safe mode where it turns into a manual mode. It cannot happen the same way when we are going to the higher levels of autonomy. So for example, for fail operational systems, you can be operating at certain duration or for certain time for duration of the failure, but it need to be for higher availability or duration of the entire system. So that's why you require higher availability overall in the vehicle. That's why for higher levels of autonomy, you require very high reliable and high available systems. Next, the current EE architectures is, as you can see, is a flat architecture where there's a gateway connected to each and every functionality of the ECU, and it communicates to each and every of the functionality within the within the car. So it takes a lot of wiring harness, and it's very inadaptable to new changes and feature additions, and also it makes OEMs very difficult to adapt to new functionalities. For example, if you want to add moving from a diesel-based engine to an electric power engine, the current architecture or the EE architecture does not support much of an adaptable transition. So every OEM is moving to somewhat called domain or zone architecture, where zonal architectures will be across the vehicle, which will allow much more of a functional integration of these functionalities. And these multiple functionalities will be combined into single ECUs, reducing the wiring harness overall, and also reducing the data movement across, which will have tremendous benefits, not from a functionality perspective, also from a cost perspective as well. Let's look at the RX microcontroller family overall. So Infineon RX is one of the most popular microcontrollers in the automotive market today. So Infineon RX has been the standard for functional safety in the automotive market. It has been based on our tri-core architecture. Tri-core architecture was designed around 2 decades ago here in Silicon Valley, combining 3 best worlds. That's the RISC architecture, DSP instructions, and real-time microcontroller functionalities. It makes the tri-core. So RX has been based on tri-core architecture. It's in production since 2015, RX, but tri-core devices are in production since 2005. We are at our latest generation, TC4X family, which is third generation of the RX microcontroller, where we are adding much more functionality or functional support to virtualization with hypervisor support, and also we are adding a lot of support in the pipeline architecture, improved pipeline sequencing, and also we are adding much support to the double precision floating point to have much more compute capabilities. So let's go over in little details of the key improvements overall in the hardware compared to the previous generations. First, looking at the workload specific compute, so we have higher performance. The clock speed of the architecture is at 500 megahertz based on our latest tri-core 1.8 architecture. And also we are adding a new accelerator called parallel processing unit for deep learning and heavy compute applications. We are improving our signal processing unit from our previous generation, at least to 2x performance for radar tree processing. And we are also improving our analog to digital converters with integrated DSPs. It's a new addition as well. Earlier we used to route the data from the analog converter peripheral to the CPU. Now we don't need to do that. We have integrated DSPs within that. Also, we are adding a new routing accelerator, data routing engine to route data between CAN to Ethernet and also process without involving the CPU. Now coming to the safety and security. Security has been one of the phenomenal improvements in our devices. With the TC4X family, we have the performance and also we have made the architecture of security very distributable across the device so that we have security at the peripheral level, security in the core level. So we have 2 individual components called cybersecurity real-time module and cybersecurity satellite. The satellite will be placed at the peripheral to support faster, secure onboard communication, and the real-time module is a separate CPU. It's called the secure CPU. Will be placed across a firewall from the tri-core cores. And with the functional safety, we continue the holistic safety concept, which we have been doing in the past generations, and we have added much more safety mechanisms to the device as well. And with the security, we are also supporting the latest ISO 21434 standard as well. Coming to the freedom from interference, we are adding a virtual machine concept, a hypervisor, a bare metal hypervisor supporting the tri-core. So we can have up to 8 virtual machines per core with the hypervisor. We have improved our context switching mechanism in the hardware, and also we have added much more protection to the core and data and the RAM as well with our MPU protection, and also we have added improvements to our DMA, which is a redundant DMA as well. And with coming to the connectivity aspect, so we have improved the connectivity overall. We are going from a 1 gigabit Ethernet to 5 gigabit Ethernet. We are adding PCIe to communicate to higher end SoCs, and also we have added security accelerators to support various security aspects. A quick look at the architecture itself. The architecture is based off the 28 nanometer TSMC node. We have, out of all the 6 cores, in the previous generation we had only 4 of them lockstep. In your current generation, all the 6 are lockstep, and new instructions are supported in the latest Tri-Core 1.8 architecture, and also a full A-B swap support. As you could see on the CPU level, we have bifurcation of flash memory A and B. And we're also adding quad SPI and octal SPI interfaces to interface with NOR flash memory. And also a new eGTM module has been added for ADAS and electrification use cases. And we are also adding CSI2 interface primarily for radar, and the signal processing unit is also being completely improved. Let's take a quick look at the machine learning accelerator, the PPU. So parallel processing unit is based on the ARC EV71. It has various scalable features from an entry to a high-end device. It has its own 32-bit scalar unit and also 512-bit vector DSP, where the most of the compute aspects could be done. We have given a lot of emphasis on the model-based development with this accelerator as well. We support MATLAB Simulink models directly to generate software for the device, and also you can program it in C++ with vector C and also OpenCL. And typically, algorithms like extended Kalman filtering and RNN, LSTM kind of algorithm can run seamlessly on the PPU since it's an SIMD architecture. Quick look at the interprocessor communication, how a Tri-Core can interface with the PPU. Here, a Tri-Core running a functionality can trigger the PPU as a coprocessor for certain functionalities, for example, to execute certain MLP algorithms, to execute certain extended Kalman filtering algorithms. And then once the request has gone to PPU will trigger back to this Tri-Core saying the activity is completed, and it will share the data. So that's how the interprocessor communication works between Tri-Core and PPU. At a quick look at the software level here, so Tri-Core is running the AutoSAR stack here with the hypervisor. You can see 3 instances of the AutoSAR stack here running, and through a complex device driver interface through the mailbox can trigger to the PPU to run certain algorithms like MLP or even Kalman filtering. Quick look at the security architecture of the TC4X family. So TC4X family, as I mentioned earlier, so security has been one of the significant improvements we have done in the device. So overall, the core performance itself is improved around 5 to 15x performance compared to the TC3X family. That's the previous generation family. And we have a distributed architecture, a satellite approach, and the secure CPU is on across the firewall, doing much more secure boot and other use cases. Here we are also supporting new accelerators like Chacha, Poly 135, and many others for new use cases in automotive. A few use cases to highlight here: secure boot, tuning protections, key management, and also firewall protection, and also intrusion detection protection mechanisms. Intrusion detection mechanism has been inbuilt in the hardware, in the peripherals, but advanced intrusion detection and prevention systems can be implemented on the PPU or the secure CPU based on the compute needs. And also we support higher SOTA use cases, and also we support authentication of the encrypted associate data, and also authentication of without encrypted associate data as well, based on the use cases. Overall, quick numbers. So overall, with secure boot, TC4X family is 20x faster compared to the previous generation, and with secure onboard communication, it's here we're taking an example of a 16-byte data transfer, around 50x faster compared to our previous generations. Quick look at the isolation features primarily. So when you move to an zonal EE architecture, you have a lot of functionalities being combined into one ECU. So you need separation of functionally for a safe and a non-safe application. Hence, we are introducing the virtual machines. It is protected by application protection unit to make sure that the safe and non-safe applications are properly bifurcated. Quick look at the software architecture here. We have 3 different applications. 2 are based on Autosara stack, and the third one is based on a third-party application. It could be motor control or any other application running on each separately on a virtual machine. Here, it interfaces through the virtual mailbox, inter-virtual machine communication, and then each of them has specific access to the peripherals which others are prohibited to access to. And quick look at the connectivity. Typically, as I mentioned, we are adding a new accelerator for data routing. We call data routing engine and CAN routing engine, primarily to move data from CAN to Ethernet, or CAN to memory. Just to give some numbers, CAN to CAN, we are in the hardware. It takes less than 5 microseconds. CAN to Ethernet takes around less than 10 microseconds, and also CAN to memory is less than 10 microseconds with our current benchmarking data. It's a brand new accelerator, which makes the CPU completely separate, and also you don't need to have the CPU for doing any data routing. It's a standalone accelerator without involvement from the CPU. And we're also improving our Ethernet MAC overall, adding some filtering and parser capabilities, and also supporting 10 base T1 Ethernet support. Quick look at different Macs. We support SGMI, RGMI, and all kind of different interfaces, with also scaling down from a 5 gig Mac to a 10 megabyte Ethernet support. And also we are adding new CAN-FD channels with some intrusion detection support as well. Quick look at the software ecosystem. Primarily to program such a complex device, you need a lot of tools, software. So starting from a pre-silicon enablement, we have the virtual prototypes already running. Currently, customers and partners are already developing software based on the virtual prototype today with the device. It supports debugging, and also it interfaces to other tools like Kenu or even Sabre, and also debugger tools. Typically, when you start your development, you need your compilers and debuggers. We continue the tradition of our rich ecosystem, which we have been having since the RX first generation. Regular debuggers, compiler support will continue, and much more will also be added in the future. And we're also enabling our IPs with new development kits, primarily for enablement for especially accelerators like parallel processing unit, and also the DSP within the analog IP. And with our microcontroller abstraction layer offering, we are also improving the abstraction layer offering from Infineon with adding some new drivers like for PCIe, data routing engine, and also 10 base T1 Ethernet driver. And we'll have new partners supporting hypervisor and also security software. A quick look at the example use case here. So consider an ADAS use case for an L1 or L2 sensor fusion, where you have sensor data from camera or radar, object data sent across to a sensor fusion ECU, which does the sensor fusion. It also does the multi-object tracking. And once it does the multi-object tracking and also does the association, it transfers the data to the motion planning algorithm, which also does the trajectory validation to avoid any collision. Once the motion planning and the trajectory validation is completed, it transfers the data to the vehicle control. When the vehicle control, it goes through its algorithm, and then once the vehicle control have an actual command, for example, a torque command to the steering ECU, and also some braking command based on the trajectory, it renders this across to the actuators. So quick look at what are the needs might be. For example, for sharing the data across from a sensor to the central compute, you need a data speed of around 1 gigabit to 2.5 gigabit for this specific use case. So where we support with our Ethernet communication and also the data routing engine to route the data to the accelerator. And also we have a security accelerator to support secure communication between the sensors and the central compute. The next aspect is to run these algorithms. Typically, you have some extended Kalman filtering, or you have some RNNs running, which can be executed on the PPU or the tricore based on the compute needs. And also for association of data, you have your joint probabilistic association data algorithms, which could also be running on the PPU or the tricore based on the application needs. Specifically also for grid processing for free space estimation, you do some thresholding and similar algorithms where a PPU could be a good fit with its 512-bit vector DSP. And also for trajectory validation, I've seen algorithms like polynomial solver or many other algorithms which could also be implemented on PPU. And typically, the vehicle control is run today on tricore because of the realistic deterministic requirements. So it could also run on Tricore and also run on PPU based on if it is a neural network based vehicle control algorithm. So typically model predictive control algorithms are run here, and then the actuation command, you require a deterministic communication to send it to the actuation ECUs, whether you use CAN-FD or Ethernet or FlexRay, Ethernet meaning 10 MB Ethernet or a FlexRay. It's supported in the device as well with secure communication. Quick summary here with the challenges I explained before. So we are trying with new accelerators apart from just the general purpose CPU. So we are adding parallel processing unit to support deep learning, machine learning, and other compute intensive applications. Our signal processing unit for radar, it's a pre-processing unit. We are improving the signal processing unit at least to power 2x FFT performance. And also we are adding new accelerator for data routing, and also we are significantly improving our security accelerators to address next generation security needs. So overall, so we have around 8K DMIPS and around 72 gigaflops of performance in ASIL-D in the device, and also we have around 1.2 DMIPS of ASIL-B performance. So this is just with accelerators. Overall, with the TC4XX device, compared to a previous generation device, we have a very high performance improvements overall with the complex compute, for example, with the PPU, with the data routing engine, with the security accelerators, and also with the CPU, supporting various heterogeneous needs. It's not a symmetric approach. With the heterogeneous approach, we also cater specific tasks to be executed on these different accelerators. And it's a optimized SOC primarily for higher connectivity with data routing engine, and also supported with the bare metal hypervisor for isolation to support zonal architectures or domain-based architectures. Next, so highly scalable parallel processing unit, which has some entry to high-end ranges. So to enable affordable AI, and also with its SIMD architecture, you can utilize for other compute needs, which is not AI as well. And with the functional safety concept, we try to improve our functional safety concept, and also we try to keep the holistic way, which we have been doing from our first generation of RX intact. We have added much more safety mechanisms in the hardware, and the security cluster, as I explained before, is a significant boost when compared to the previous generation. Then it's a highly scalable platform. From a TC4X, we have a low-end device to a high-end device enabled with our rich ecosystem primarily. It's not easy to program such a complex device, so we have made effort to make sure that higher programmability is given into consideration, and you can program it very high-level programming languages, and also applications use cases easier and faster. With this, I'll end my talk. Thank you.
Thanks, Ram. So a few questions have popped up. One that seems to be quite popular is object detection done off chip? And the reason for that question is the diagram on slide 35 shows object data coming in, or is that just raw sensor data, and is the object detection done on the chip?
So this specific use case, I took the object data example. This is the object data. I would say, so camera, for example, an intelligent camera and the front and the radar is detecting an object. But once you send the objects with the sensor fusion, you could be able to classify the data as well with the object primarily.
Okay, so that
on the
sounds
device.
Like the object detection is actually being done elsewhere. Is that correct? At the camera? Or
yeah, in this specific use case, you're right. Yeah, it's done on the sensor level where the radar ECU, but the RX device can do that as well. But this use case I've taken as sensor fusion use case. Yeah.
I see. There was another question about how exactly you go about getting ASIL-D on the PPU. Is that through lockstep or through replication or through something else?
Yeah, lockstep is the crude way to achieve it. We have some different mechanisms. I cannot share the details now, but it's not completely through lockstep. We have different mechanisms in place in the hardware where you could achieve ASIL-D up to system level. Yeah.
I see. Okay, so it's part of the secret sauce then. All right. There's another question that relates to the tools. So this is from Andreas Farber, who says, I noticed you list neither GCC nor LLVM compilers for Tricore or PPU. Could you comment on that?
We are also looking at LLVM-based compilers. I think in our previous generation, we had one of our compiler vendor implement the LLVM-based compiler as well. But for PPU, we are also looking at that. So we will have LLVM-based support as well. Yeah,
Okay.
that's the current idea.
Good. And I kind of had a general question on your design. So when you were putting this together, the safety and security sometimes conflict in terms of their design objectives. How did you go about balancing those, and what sort of trade-offs did you encounter?
Right, very good question. So primarily, so there are two aspects, right? For example, how do you make sure the device is not compromised at all levels from a security perspective, and also due to any systematic faults or random hardware faults, you're not compromising the functionality of an ECU, right? So we have different goals at the top level. So typically, when you design based on ISO 26262, you have your safety goal, but with 21434, we also consider the security goal at the top level as well. So both go in hand. So any compromise to the security can also compromise the chip, so which is a violation of safety goal as well. So that's how the design methodology has been from the scratch. So that's what we plan to implement as well.
And is there some kind of introspection that's around to determine that the system is being attacked at some given point?
So we have looked at different kind of attacks. For example, for a different kind of attack, it's a different approach. For example, for spoofing, you have to have a different approach. For a side channel attack, you have to have a different approach. For repudiation, you have different approach. For read kind of attack, we have done the proper, what you could say, TARA or analysis to make sure that how the device can be supported. And some attacks, for example, for side channel attacks, you need to also have the software in place to support this side channel attacks as well. Hardware does not have the side channel inbuilt features, but it supports all the necessary elements required by the software, and software can implement the side channel attacks with the efficiency of the hardware inbuilt.
I see. So there's a question as well about how, a similar question relating to reliability. So in a high reliability system, you may have hardware failures of various sorts, and those are both safety and security problems. And so how does the system manage those?
Yeah, so there are two aspects to that, what we build from our chip level and what our users build from a system level, right? From a chip level, we also make sure from a dependability perspective, we also go through the extensive testing of AEC-Q100 to make sure it's supportable across temperatures. Just an example, it requires 1,000 hours of stress testing for the device for the AEC-Q100. So the devices can go up to grade 0, grade 1, or grade 2, depending on the use case there. So what we do from Infineon perspective is that we go through up to 6,000 hours of testing instead of 1,000 hours to make sure that the device is reliable, device is safe. And you could look at our PPM numbers, which is very, very low. Okay,
so just to remind our audience who may not be familiar with grade 0, 1, and 2, what do those categories mean?
Yeah, grade 0, the junction temperature can go up to 170 degrees. So the junction temperature and the nominal temperature is around 150 degrees, yeah.
Okay. And so you mentioned you were using 28 nanometer. What special design considerations did you need to take into account to get it to exist at 175?
170, so the thermal aspects, I cannot discuss much details because it's the new device coming up. We'll have the device later this year. So I'm not allowed to talk about the thermal aspects.
Fair enough, okay. There's a question from Columbia University on, do you have any countermeasures to protect against software vector attacks such as buffer overflow?
So we have some techniques in the hardware as well. So for example, buffer overflow, everything can be also protected from MPU mechanisms in general, how you implement your MPU mechanism overall. So if you have a safe application running maybe for providing an assist to the electric power steering, right? So you have proper code and data set for your specific application. It is not allowed to go beyond that specific memory. If it accesses anything beyond that specific application or specific core, then it will generate a trap, and you will have a safety violation at that time. So you will not have any buffer overflow or any kind of attack specific to that in the hardware based on your configuration.
So that's a hardware feature, or that's something that the
MPU is the hardware feature. MPU is the hardware feature. User has to configure how much memory I can allocate for this component, and it should not go beyond that from both from a memory and from a timing budget. For example, if you set timing budget saying that this has to execute within 10 milliseconds, so if it violates 10 millisecond timing maybe for 3 times, you can set as a fault, and system will be notified that it is violating the goal.
I see. Okay, very good. I think we are getting close to out of time. So I guess for the final question, what was kind of the key? Oh, here we go. There's one that's just popped in that I'll ask instead, which is, how do you avoid being surprised by aging failures?
Could you repeat? Sorry.
So as the device ages, so your 6,000 hours is meant to simulate lifetime. How do you handle degradation? Is it just designed out of the system, or is it actually designed to degrade gracefully over time?
So what we do is that when we do our design, for example, for P-Flash and data flash, we have certain cycles limitations we have provided to make sure that this can be run for maybe 20 years, right? And within certain durations. For example, we have certain program flash cycles and data flash cycles, you can execute them. But also I've seen some intelligent mechanisms in software, for example, for data handling to avoid aging or even wearing out data. What we typically do is that we take a buffer approach and we call it flash emulation of EEPROM. And we take two buffer approaches and we write into different buffers so that you don't wear out the same cell again. So you write it in conjunction so that you can avoid aging of the cell as well. And it's also considered in devices because these devices, once designed in an automotive system, can go for 20 years, right? So.
True. Excellent. Well, thank you very much for a great talk. And I guess we look forward to seeing this chip in operation. There's a lot of virtual applause on the Slack channel. So.
Thank you very much. Thank you for the questions.
Thanks very much. The second talk in our session is on architecting an open RISC-V 5G and AI SoC for next generation 5G open radio access network. And that will be given by Sriram Rajagopal from EdgeQ. Sriram has 17 years of history as a systems architect in wireless communications. He's worked on both endpoints of the network, UE's and base station. His career spanned from designing and deploying industry-defining 5G massive mobile systems for wireless operators to working on mass schedulers and system designs for large-scale systems to physical layer algorithms. In his current role, systems design at EdgeQ, Sriram is responsible for architecting the world's first 5G AI base station on the chip that we shall hear about coming up. Prior to that, he was a distinguished engineer at Altiostar Networks and drove mass market field deployments and had several optimizations. As head of physical layer systems at Redeem Communications, he also led the design and deployment of the world's first 4G UE, WiMAX. Sriram has 10 issued patents and 5 conference publications. He holds a master's degree in EE from Stanford and a bachelor's in communication engineering from the University of Madras.
At HQ, we are one of the newest semiconductor companies emerging in the field of baseband processing and modem technologies. In fact, we have only recently come out of stealth in late 2020. I am extremely excited to be unveiling our first software programmable 5G plus AI SoC built on Open RISC-V at this year's Hot Chips. For those unfamiliar with HQ, we are pioneering and leading innovators in 5G base station on a single chip. With distinguished pedigree from Qualcomm, Intel, and Broadcom, we have been pioneering 5G plus AI convergence on a single SoC, which is completely programmable and customizable. We have been extremely blessed to be supported by industry luminaries in the field of wireless and compute, such as Paul Jacobs, ex-CEO and Executive Chairman of Qualcomm, Matt Grob, ex-CTO of Qualcomm, and Professor Kozarakis from Stanford University. Let me take a brief moment to talk about the accomplishments of my peers and colleagues. We have delivered more than 8 generations of modems on 50 plus SoCs in this space. This finds its space in almost all the Apple and Android products. It is safe to say that we have been behind the wireless revolution on Wi-Fi, 4G, and 5G. As for myself, I'm Sriram Rajagopal. I'm Head of Systems Engineering at EdgeQ. Today, I'm going to be talking about architecting a 5G plus AI SoC based on Open RISC-V processors for the next generation RAM. What is 5G? This is essentially 5G in a nutshell. 5G is going to enable connecting the next trillion of users with new services and with a completely new architecture. 5G is based upon three pillars: high reliability and robustness, high density of connections, and high volume of traffic. Different network deployments require different services from the network. As we can see, in some cases there is a requirement for high speed and mobility, such as rail networks or roadways. There may be requirement for low latency of access and robustness, such as industrial applications. There may also be need for high volume of traffic, such as urban dense deployments. Spectrum, as you can imagine, is a very key resource for wireless technologies. 5G will enable all of these services based upon expansion of new spectrum, be it in unlicensed band such as millimeter wave or private 5G, or even in the licensed band. Let us take a look at the progression of the RAN network over time. Even if we had discrete components such as a radio sitting on top of the tower and a baseband unit at the bottom or at a central location, traditional networks have always been about proprietary hardware and proprietary software running on top of them, connected by proprietary interfaces. Even with virtualization or vRAN, it has been about proprietary software with virtual functions enabled, running on proprietary or commercial hardware. This is very rigid and inflexible, not allowing for innovation or expansion, the kind of expansion that 5G requires to fully utilize its potential. Now let us see the Open RAN system. It is based upon commercial off-the-shelf hardware from any vendors and software also from any vendors, allowing for virtual functions to be enabled. The key point allowing this to actually work are the open interfaces between these modules. There has indeed been two tectonic shifts over the last few decades in this field. One is migration to a cloud-native model, and the other is a complete disaggregation of hardware and software. Let us take a look under the hood of an O-RAN base station. If you see the flow on the top, it talks about all the different components and modules and functionalities as supported by the O-RAN base station. Let us start on the receive on the right side. RF signals are received by the radios which are mounted on top of the base stations, and these are converted to digital samples by the radio operations, and these digital samples go through some signal processing operations such as filtering, removal of cyclic prefix, and FFTs to convert these digital samples into frequency domain symbols. This whole unit, as you can imagine, is called a radio unit, as it does radio operations. These frequency domain symbols are then sent to another entity in the network, which does further signal processing operations as defined by the standard. These include channel estimation, equalization, maybe beamforming operations for massive MIMO systems. There is also FEC acceleration, which is forward error correcting codes for decoding the bits. These bits are then converted to packets, which are processed by standard defined procedures for MAC and radio link control. Any radio that is deployed would serve connections for multiple users. The scheduling for these users, such as which frequency bands to use, when different users need to be scheduled, are also part of these MAC operations. This entity is called a distributed unit and is deployed across the coverage area, but it does connect to multiple RUs. These packets are then sent to another entity in the network, which is called the central unit. It essentially does IP packet processing on the data side, as well as connection management for the different users and mobility management on the control side. These different operations have been classified or segregated into different entities so as to optimize the control and the data traffic between them. These segregation points are usually called as the O-RAN splits. Now that we have seen the different components, let me summarize based on the hardware architectures. The RU does specialized operations for radio frequency conversions and some digital signal processing, and hence runs on specialized hardware. The DU follows a hybrid architecture because some of the operations are for specialized signal processing, run on specialized hardware, and some of the operations for packet processing and scheduler operations run on generic processors such as x86 or ARM. Similarly, the CU also runs on generic processors doing connection management and other IP level packet operations. As I mentioned, the key important factor for all of these are the open interfaces between these entities. The interface between the RU and the DU is called the front hall, and the interface between the DU and the CU is called the mid hall. Having these open interfaces allows for a rich environment of multi-vendor, and each vendor can focus on their each special operation. Now that we have seen the many different components of an open RAN base station, how does one go about designing any one of these? Let us start with the RU. As we have seen, RU does radio operations of converting the RF signal into baseband signal, as well as it does some signal processing operations such as cyclic prefix removal, filtering, and FFTs and IFFTs. So for the RF, we have specialized hardware because this is a very niche domain for specific bands and bandwidths. We would need interfaces to connect with many of the RF vendors that are available. Commonly available interfaces are JustD, and also you could design your own analog IQ interface as well. The signal processing entity needs to be completely programmable in order to allow for the different operations that a 5G can support. Along with this, we also need to send these frequency domain symbols from the RU to the DU. This is supported by the ORAN ECPRI protocol, and we would need to build this interface as well. Correspondingly, on the DU, we would also have the same ORAN interface to receive the packets on ECPRI from the RU. Along with this, we would be running specialized signal processing operations for channel estimation, beamforming, equalization, and so on a completely programmable DSP engine. The forward error correcting codes, or FEC, for encoding and decoding are essentially a very compute intensive with not much innovation and completely standardized. So this can be a programmable but an hardware accelerator. The bits which are being generated from here need to be processed by an external host processor, and hence these bits need to be transferred to that external host, and an interface for this also needs to be built in. Now we can see a converged SOC emerging from all of this. We would need interfaces to support the radios, interfaces to support the connection between the RU and the DU, which is ECPRI, and also an interface to support the host, which is doing general purpose processing. Along with this, we would really need a programmable DSP engine, some hardware acceleration such as FEC, and also a general compute for management of the system, as well as running the full L2, L3 stack in case of a converged 5G solution also needs to be built in. With that, I present to you the world's first 5G base station on a chip. In this block diagram, we can see the different subsystems on the chip which are connected by an interconnect. The signal processing complex, which is a multi-core specialized baseband processing based on RISC-V instruction set with 50 plus custom extensions. CPU subsystem, which is an 8-core ARM Neoverse CPU. The protocol accelerator, which supports data path L2, L3 accelerations for MAC and cryptographic processing. The FEC acceleration for forward error correction codes and bit level processing for the different standards. The RF interface with support for ADCs and DACs and up conversions and down conversions, and support for channel sense, AGC, as well as DPD and CFR. And most importantly, but not the least, is the IO subsystem, which has controllers for connecting to the different other devices we talked about, such as PCIe, USB, Ethernet, ECPRI, and JustD. Building a complex system such as this, there are always trade-offs between adding more features versus the area. We have solved this problem in this chip by having almost the same split as required by the ORAN across the different subsystems in this system. By providing for a fast interconnect between them, we can always scale up or down the different subsystems in order to achieve the kind of performance that we need. Additionally, if more compute power is required, then we also provide for an interconnect so that different chips can be ganged up together for increased processing. This is massively parallel completely programmable with open source tool chains and allows for different configurations on 5G, AI, and also supports network processing and general CPU processing. Let us now look at the heart of the EdgeQ chip, which is the DSP complex. This is a multi-core RiskFi scalar baseband with multi-stage pipeline for the arithmetic unit with custom instruction extensions. The extensions are done for baseband specific processing for different operations of the wireless standards. We have also converged many operations such as nonlinear approximations to support both 5G and AI. This can be easily programmed for performing operations as a DU or RU or even as a complete G-Node B. As you can see, the standard RISC-V processor allows for execution units, instruction memory, data memory, L1 cache, branch prediction, memory interfaces, and so on. The custom instruction extension is used to develop the arithmetic unit with extensions that include operations for FFT, complex modulations, nonlinear functions, matrix decompositions, equalizations, and so on. This allows support for both 4G LTE and 5G NR as well. Having seen all of this, so what can this chip do? The DU performance under different configurations for the EdgeQ chip is shown here. 5G allows for many different configurations to be deployed: sub-6, millimeter wave, small cell, macro cell, and so on. In this chip, all of these configurations are completely programmable and software upgradable. Fundamentally, this chip can do 400 megahertz worth of processing with 44-hour systems. So in the NR world, it consists of about 4 carriers each of 100 megahertz supporting 4 antenna systems, achieving up to 10 Gbps of throughput. This chip can also support massive MIMO accelerations such as 32 TRX antennas. Massive MIMO systems require beamforming coefficient generation and sounding reference signal processing, which are additional intensive operations on the chip. For this configuration, we would be able to support 2 carriers of 100 megahertz each and going up till 10 Gbps again. For further intensive processing of 64 TRX operations, we can gang up to 2 chips to be able to support 200 megahertz worth of processing for achieving 20 Gbps of throughput. As a programmable chip, it also supports millimeter wave systems. With millimeter wave, we can support up to 400 megahertz of processing on a single carrier, achieving up to 5 Gbps of throughput. I have talked about the different modules or components of the Open RAN base station and also talked about the different blocks or subsystems on the EdgeQ chip. Now I will map the two together for you. This is an RX receive flow, almost a life of a packet within the chip. We can start on the right for the receive processing, where there is an RF interface which could be either just D or an analog IQ interface. This is an hardened IP in order to do all the filtering operations and doing the RF imbalance corrections, where we support DPD and CFR as well. These digital samples are then stored on the signal processing complex in the memories, where signal processing operations such as cyclic prefix removal and FFTs are performed. If this was an RU alone, then these samples would be converted to an ORAN eCPRI packet and sent over the Ethernet. And this is where the soft programmable eCPRI engine comes into the picture. Similarly, on the other side, on the DU, we would be receiving these eCPRI packets and going through a decompression operation in a completely programmable DSP complex. This is followed by other signal processing operations such as channel estimation, equalization, and so on. These are then sent over to the FEC engine, where they are converted to log likelihood ratios or LLRs and then decoded by the hardware, which is a FEC engine. These bits are then sent over for further network level processing at the higher layers, which are running on the ARM CPUs. These are then sent over to the core network via the Ethernet interface on the NG interface as defined by the 3GPP. For the first time in cellular history, 5G and ORAN present an opportunity for profound reinvention and disruption. My talk today represents that vision that we have held at EdgeQ for about 3 years. I am extremely glad to announce that it is not a vision anymore, but it is a reality. With that, I present to you EdgeQ's 5G base station on a chip. It is a single chip with multiple play on DU or G0B or even as an RU. These chips are sampling now, and I would like to thank Hot Chips for having us this year.
So there are some questions. So
Good.
the first
Yeah, I'm here.
there we go. Apologies, apparently electronics is not one of my forces. There's a good question on what's the process node for this chip?
Yeah, we are actually not disclosing that publicly right now, but we are TSMC FinFET. So
Okay, so TSMC somewhere. And you may not be able to disclose some of these other questions either. So which Neoverse cores are you using, and what frequency are you operating them at?
so we are using Neoverse, the E1 cores, and we are operating them about 2 gigahertz.
Okay. And what's the what range for total dynamic power for this chip?
So power is one of those things, again, we are not really disclosing publicly, but this is going to be sort of unprecedented power for a base station implementation on an SoC. As you heard me talk about earlier, we have background from the UE side as well. So we've made it a very conscious decision to keep the power really low, and that's been part of our DNA. So we do expect to be very, very competitive on power, especially for a 5G base station implementation. Maybe in the teens is what all I can say.
Okay, very good. And it's interesting that the chip uses both RISC-V and ARM. Can you comment about the particular RISC-V that you're using? Is this a standard implementation of some sort? Did you make your own? Where did it come from?
Yeah, so we did license the RiskFi IP, and this is from Andes. But almost all the functionalities are, as you can imagine, from an open source almost. Yeah, we haven't done, we haven't asked for any specific operations from them, but most of the value add that, as I talked about, has come from our own implementation of the custom instruction extensions. So
you mentioned that there were 50 custom extensions.
Yeah.
What kinds of things do those do?
So this is where we do the convergence of the 5G and the AI, where we envision the convergence to work out. Essentially, when we are talking about either 5G or from an AI, a lot of the operations are, to a large extent, we see a lot of parallelism. What are they? Nonlinear operations, as an example, could be when you're doing, at least on the AI side, you may need things like ReLU, or tanh functions. On the modem side, you need inverses or ATANs as an example. That's one aspect which we've done extensions for. The most important or the critical one essentially are the matrix multiply, the complex matrix multiply, matrix or matrix vector inner products. Additionally, on top of that, we've done, the modem, especially if it's an OFDM system, FFTs become a very, very crucial part of that. So we've done extensions for FFTs, starting from the butterflies, Radix 2 or Radix 3, and so on.
So would you expect future or other ORAN designs to use similar instructions, or these exact same instructions, or something else? How would you expect the ecosystem to evolve over time?
That is very interesting. So we want to be path breakers in this field, and I think that this is almost the first RISC-V extension that we have for a modem implementation, and the modem in this case is being implemented on for the base station aspects of this. There are a lot of parallelism. While I did not talk about it in this talk, almost all of these, because it's software programmable, we could almost use it even as a UE or a CPE or so on and so forth. So there is possibility of using similar. So we've nailed it down or filtered it down to thinking these are the core functions that are needed for a modem, whether it's a base station or whether it's a UE. There are a lot of similarities. So The ecosystem can evolve. We would also be looking at contributing back, but over a period of time, not immediately. A lot of these extensions that I talked about are common functionalities. I'm sure, and as I talked about, all of these things, people may find similarities and do the same themselves. But from HQ's point of view, it may take some time for us to start contributing back into the open ecosystem. That's where the benefit lies here, right? The open ecosystem. A lot of people are looking at it, and they can see what works for them. Yeah.
Nice. So if you look at the chip, so what you've designed is kind of a software-driven chip versus a hard-coded SoC implementing similar functionality. How did you make those trade-offs? Where did you kind of choose where in that spectrum to pin the design?
Yeah, one of the key aspects of 5G essentially is that there are just too many options, right? And you can almost get overwhelmed by saying, hey, there's so many things, and I want high performance as well. So if you go down that path of saying, okay, let me hard code for this and let me hard code for that, then you almost have a single SoC for one particular sort of a slice, which is, say, IoT. And then you have another sort of implementation or design for another application, which is high mobility. So the aspects which are, so this is where sort of knowledge, understanding of 5G, and that's where what our team brings in. So you need to know what things, vary or change within the 5G framework itself and try to make them soft. So all of that almost trickles down to having a control software which is programmable, so that we can implement the different variations of the standard or even future enhancements that the standards may have. The aspects which don't have much innovation, where we don't see much changes, essentially include bit level processing, which is encode and decode operations, which are standardized. Sorry, do you want me to repeat that, Rob?
No, carry on.
Okay, so the bit level or standard level processing are standardized, have been standardized for a long time. There's not much innovation to be done. So those are accelerated. And as I said, even for us to achieve in a very short symbol time, which is much less than, say, 16 microseconds, or in fact in millimeter wave, it's like 8 microseconds, FFTs and so on need to be accelerated. So that's why we took the RiskFi processor, added hardware, custom extensions, so that we can implement these. So these are two aspects that we considered in our design.
Okay, so one final question for you. If you're looking at, is this a small cell kind of thing, or is it something that goes on towers? It's a base station on a chip. What sort of base station is it? What's your target?
Yeah, so we, as I was mentioning, this chip as performance, I mentioned the performance. It was a DU performance. DU is essentially, a macro cell. And in fact, we are aggregating not just one, but we are aggregating many more than, one macro cell. We, there was a slide which talked about the different performances. We could do, 4 fully loaded carriers of macros within the same chip as a DU performance, or even massive MIMO systems. So that since we have the ARM processors as well, if required, we could do a complete G Node B within the same chip as well. We can run the L2, L3 stack on this as well. So from a physical layer acceleration perspective, so this could do a complete stack up to 10 Gbps of throughput, downlink and uplink. So it could be a macro, it could be a G Node B, it could even be an RU, because we have the interfaces to connect to RFICs to support that as well. So it's all the spectrum, the complete spectrum in 5G.
Okay, so if you built a cell tower, how many of these would you need roughly?
So so as I said, so we need one chip to be able to support one sector, which is 3 cells, right? So a single chip would be able to do a single tower easily.
Okay, very good. All right, well, thank you very much. This has been a very interesting talk, and your chip is pretty exciting. So again, thanks very much for presenting.
Thank you.
Our final talk in this session is on the Aquabolt XL, which is the Samsung HBM2 PIM with in-memory processing for ML accelerators. It'll be presented by Hyun Kim from Samsung. He'll be giving the talk, and then Namsung Kim will join us afterwards for the Q&A session. So Jin is a principal engineer in Samsung's DRAM memory planning and enabling group. He's been with Samsung for 24 years, looks like, joined in 1997. He says, dozens of memory-related patents, which I do not doubt, and he's presented at HopChips previously in 2016. So with that, let's see what Hyun has to say.
Hello everyone, nice to meet you. My name is Hyun Kim. Today I will present Aquabolt XL, Samsung HBM2 PIM with in-memory processing for machine learning accelerator and beyond. I'm in charge of processing in-memory architecture, standardization, system enabling, and marketing in Samsung Memory Division. Before presentation, I really appreciate the great key players I can't reveal, and especially Facebook for AXDIM and Xilinx for HBM PIM. We have been working with chipset companies, national labs, and data center vendors on a wide variety of different platforms. Firstly, we will focus on the detailed PIM hardware architecture, software support, and then how we'll build the target chip and integrate for several systems. In general, processing in memory is one of the future memory technology, not only specific memory device. So, finally, we are going to propose extended next PIM memory solution, such as LPDDR5 PIM for memory application and acceleration DIM for DIM level PIM application. New application of future have required higher off-chip memory bandwidth. However, due to the physical constraint of chip package and system board, it is very expensive to further increase the bandwidth of off-chip memory. In order to cost-effective bandwidth improvement and energy efficiency, industry have begun to rethink and further advance the processing in memory architecture of the past. Despite the recent advance, no memory vendors has developed PIM memory, even a proof of concept silicon yet. The reason is that past PIM architecture often require change to the host processor or the application code that were not easily controlled by the memory company. Basically, our target is to utilize the internal memory bandwidth to improve performance while increasing energy efficiency without this kind of change. This is achieved by reducing the distance between computing and memory, or by integrating memory element into the memory itself. Most of systems require fast, low power, and high performance commercial memory simultaneously. This is target area for PIM. So many attempts have been made to subdivide the memory hierarchy to solve the bottleneck, such as the near-far memory. But the development of memory media was not realistic enough to threaten the existing commodity memory. And only domain-specific memory solutions have existed. For example, in package memory, rest level cache memory, high capacity storage class memory, and so on. To make matters worse, only the memory hierarchy is increased without the performance of media itself, and this kind of memory hierarchy interfaces heavily consume more energy than the existing memory. In order to solve this fundamental problem, we will propose processing in memory in various memory hierarchy. Aquabolt XL HBM2 PIM is Samsung's implementation of in-memory processing with selected arithmetic operations. Central to this technology is the significant bandwidth multiplication that achieved through concurrent operation of computation engines built inside the internal memory banks. The core benefit are performance uplift of bandwidth-hungry workload, as well as energy saving from reduction of the compute-to-memory data movement. PIM is an architecture that can be adopted on all of commercial memory products. The first demonstrator vehicle is this technology is based on the HBM2 Aquabolt, which is used in leading edge AI and HPC systems. The programmable computing unit, PCU, is integrated with the memory core on a single chip to enable parallel processing and minimize data movement. Typically, most of the emerging application workflows show bottlenecks in computer side or the memory side or I/O. Modern parallel processors, such as GPGPU or the AI-centric processor, are typically designed to accelerate high-density computing. They are high performance at the compute boundary layer, but consume significant time and energy to process memory-bound operations with low arithmetic intensity. On the other hand, our PIM architecture can excel in these features, make it a natural component to the host for the optimal system balance and performance per watt. When offloading memory binding operations to the in-memory engine, this new architecture can deliver more than 2 times system performance while reducing energy consumption by more than 70% watt for memory-bound workloads, such as speech recognition, natural language translation, recommendation, and so on. This slide is for those unfamiliar with the basic HBM memory. Samsung's first implementation was in the form of HBM. Back to the example, SIM the floating point unit has been placed at the bank I/O boundary to enable access to multiple bank floating point unit in a lockstep manner. We put SIM the floating point unit near the bank at the bank I/O boundary to fully use bank bandwidth, which is located nearby I/O sense amplifier arrays. Each floating point unit is connected to I/O sense amplifier and the write driver and the interface with RISC files. However, we preserve the DRAM bank control signals and the corresponding logics. Now, let me introduce the Aquabolt XL microarchitecture. Each PIM unit consists of 3 major components, which are floating point 16 SIMmed floating point unit array, RISC files, and PIM unit controller. SIMmed floating point unit array performs 16 FP16 operation on concurrently. The data used in the operations can be fetched from data bank, general RISC files, or scalar RISC files. The instruction for PIM operation can be stored in the command RISC files, and PIM unit controller controls the all operation of PIM unit, such as fetching, encoding, controlling pipeline signals, and forwarding. In the PIM mode, external data commands such as read, write, increase CRF program counter, and read or write the data at the same time. In terms of instructions, 4 arithmetic, 2 data transfer, and 3 control flow operations are currently supported. But this list is open for discussion, and Samsung would like to work with memory vendors, SIP partners, and customers to define a standard. The discussion would naturally include not just the operation itself, but also the precision, register, instruction format, and so on. Our PIM DRAM supports a typical RISC style 32-bit instructions. We implement all bank control logic to support all bank operation mode, where the bank address of a given column address are ignored. And the same row and column of all banks are currently accessed in the lockstep manner by a single DRAM command. In a all bank mode, HBM PIM with 16 banks per pseudo channel can provide 8 times higher on-chip compute bandwidth than standard HBM. In the all bank PIM mode, a DRAM column command triggered execution of a PIM instruction in the CRF, and then update a PIM program counter to get the next PIM instruction. This approach is comfortable with any processor adopting JEDEC compliant DRAM controllers, because it relies on standard DRAM command. One of our design philosophy is to make it possible to enjoy the benefit of PIM technology even when running existing deep learning models without any software modification. The execution path for that is indicated as a native execution path in the left figure. To this end, red blocks are added to the existing machine learning software stack. Additionally, in order to enable the application programmer to use PIM easily, we also developed PIM custom operation. The execution path using it is indicated as a PIM direct execution path in the right figure. In order to implement PIM on the silicon level, we replaced the cell array area with the PIM execution block for design convenience. Also, we replaced the bottom 4 DRAM dies of 8-high HBM2. After that, we assemble to one package and the SIP to a commercial GPU FPGA processor. We implemented it with 20 nanometer DRAM technology and integrated it with an unmodified commercial GPU FPGA processor. Also, we developed the necessary software stack and can run existing applications without changing their source code. We evaluated the performance of the HBM-based PIM system using bus, micro benchmark, and end-to-end applications. We used the matrix vector multiplication and element-wise add micro benchmarks, DeepSpeech2, RNNT, and GNMT for natural language processing application, and AlexNet and ResNet for computer vision applications. In the figure below, the blue bar represents the performance gain on each benchmark from the PIM system compared to baseline. As summarizing the key result in the single batch case, PIM system give up to 8.9 times higher performance than the baseline. It showed high performance improvement of GenV micro benchmark and also in the NLP end-to-end application where GenV is mainly used. For the element-wise operation, such as add, increasing batch size does not increase the data reusability. So the performance gain is the same on all batch size. We also measured the power consumption of fabricated Aquabolt XL HBM2 PIM and found the Aquabolt XL consumed only 5.4% higher power compared to the HBM, despite not changing the buffer die. Multiple PIM execution units operate at the same time, so the power consumption of DRAM internal component increases, which are presented as a gray and blue color. But at the same time, power consumption of internal global I/O bus, the green color, considerable decrease because there is no dynamic consumption for global bus. The power consumption of buffer die and I/O PHY, which is the orange bar, decrease, but not dramatically because we didn't change the buffer die. If we can modify buffer die for PIM, the power consumption of HBM PIM can be reduced further. We evaluate the performance of real-life system using TensorFlow implementation of DeepSpeech2, which is a voice recognition application. For dataset, we use LibreSpeech ASR corpus, which is the open source corpus of read English speech. You can see the recorded real-time video or demo application. Normal HBM2 is used the left clip, and the HBM PIM is used in the center clip. The demonstration UI contains current voice waveform, source text, and the recognized text from voice. In addition, UI also showed trends and statistics of inference rates and word character error rate. It's the initial stage, so there is still room for optimization. We also plan to accelerate more memory-bound applications. We also measured the power consumption on the DCP2 execution because the processor utilization in the PIM system decreases. The average power is reduced. At the same time, HBM PIM reduced the execution time of DCP2 by acceleration, so that energy efficiency increased significantly. We extended our PIM platform from GPU to FPGA for the flexibility. For fair comparison, we created two separate Xilinx Arbor U280 project, baseline and HBM PIM. PIM system guarantees the correct order of PIM-related memory command. Our baseline and the PIM accelerator was designed to accelerate the maximum HBM bandwidth. Below architecture is the high-level PIM evaluation architecture on the FPGA. We will cover the PIM evaluation result on Xilinx Arbor U280 FPGA system. We evaluated the performance of the FPGA-based PIM system using BAS, micro benchmark, and end-to-end application. We used the matrix vector multiplication, vector-vector add, and GenV matrix-based LSTM for micro benchmarks. As summarized, the key result in micro benchmark case, the FPGA-based PIM system performs 2.82 times higher performance than the baseline in GenV. Also, add and LSTM micro benchmark result show the performance gain of 2.85 times and 2.54 times respectively. As I said, the previous slide, we evaluated the PIM performance of FPGA-based system using RNNT end-to-end application. RNNT application is mainly composed of LSTM models in left pie graph. LSTM layer consumes around 90% of the running time, while vector matrix multiplication kernel used around 80%. As a result, PIM-based FPGA system is able to deliver around 2.5 times system performance while reducing energy consumption by 62%. PIM can be applied to not only HBM but also LPDDR5 for low power applications. RNNT speech recognition model, transformer-based translation, and GPT-2 text generation show the performance gain of 2.3 times, 1.8 times, and 2.4 times respectively. And energy efficiency improvement was 3.9 times, 2.2 times, and 4.4 times respectively. But compared to GPT-2, VIT showed performance and energy gain of around 10% because it was composed based on the computer-bound transformer encoder. However, many computer vision models such as Image GPT and IPT are configured based on the transformer decoder, like GPT-2. This means that vision model can also be accelerated through processing in memory. We expanded evaluated based on the analytical model, transformer, and RNN-based natural language processing still show the high performance and energy gain. It should be noted that CNN-based computer vision, which is relative computer-bound, also show the performance gain by applying PIM to +1 operation. For example, Deep Lab V3-based video bokeh model had plus 20% of performance gain and plus 30% of energy efficiency improvement. We have been asked many questions in common while collaborating with the industry, so I need to describe only 3 questions. We can scale over from component level to DIMM level PIM. Acceleration DIMM, AX DIMM, can maximize the length level parallelism by using all length activation to overcome bottleneck of existing DDR channel. There are many concerns regarding system performance, which is about CPU, memory data movement bottlenecks. Firstly, length level parallelism is needed to improve system performance. XDIMM provides a specific acceleration function in AXDIMM buffer. Similar to HBM PIM case, AXDIMM can reduce the data movement energy by utilizing in-DIMM data processing unit as well. As mentioned earlier, since drop-in replacement is required without changing the echo of CPU and application software in AXDIMM, it was developed to operate by adding only a blue box in the software stack, which are AXDIMM API, library, and device driver. Our approach indicated that plus 80% in two-rank case performance gain, utilize up to higher in DIMM bandwidth by multi-rank parallel operation, and 42.6% in two-rank case, and a saving compared to normal RDIMM system. This is the AXDIMM evaluation system and result. Since AXDIMM exploits the rank level parallelism, the memory bandwidth will be scaled linearly with the number of lengths under the memory channel. We validated the speed up of embedding operation on AXDIMM from the expanded memory bandwidth. In left figure, we shift the size of memory footprint of the SLS operator by batch size from 4K to 128K. The AXDIMM system achieved plus 70 to 80% latency speed up by utilizing the double internal bandwidth of two ranks on AXDIMM. Regarding energy gain, AXDIMM system also demonstrates a significant memory energy saving by reducing the data movement between the host and the AXDIMM, performing the embedding pooling in the memory side. Recommendation near memory processing logic makes better performance for SLS execution. Actually, it achieved plus 80% SLS execution, speed up DLRM application. If we sweep number of lengths, we can observe more than plus 80% QPS gain, and it will increase by length, which is 3.5 times, 6.9 times, respectively. Before concluding this presentation, I will talk about the future PIM DRAM. First, we will focus on the PIM standardization through JEDEC, like other DRAM products. We have already opened the specific feature in JEDEC. The second, we need a better ecosystem for wide range algorithm and applications. We want to create together with the customer who will enjoy PIM technology. The third, the spreading PIM to other DRAM types, like as a DIMM level, LPDDR, and the future memory device from edge device to data center system with wide numerical format. Lastly, PIM will continuously show higher performance with lower energy consumption by enhanced DRAM process technology. PIM is not limited to a specific DRAM processor or the product, and the relative performance and the energy reduction compared to baseline is always possible. Thank you for your attention.
Very good. Thank you for that talk. Our Q&A part will be handled by Namsung Kim, who is well known to the Hot Chips community and Senior Vice President of Samsung's memory business. He's been doing an admirable job on the Slack channel, but there are a couple of questions that have popped up that I believe are kind of fit into this question of how does a PIM-aware software stack work? And in particular, how does the PIM implementation manage coherence with a host?
Okay, that's a great question, and it's often asked by many other people. So basically, the memory region that will be uploaded to processing memory will not be cached. And for those applications, anyway, they have a very low data reusability in the cache. And actually, by making them uncacheable, in fact, you can improve the overall system performance because such data actually pollute the cache. So by making those regions uncacheable, we deal with the cache coherence. And also another aspect is for the processing in memory instruction, one instruction is executed by one memory command, which corresponds to load or store instruction. So all the operations within the processing memory is very deterministic, and the host CPU or GPU can know what's exactly going on inside the processing memory.
Okay, and so what does that look like in terms of the host when it issues an instruction that it believes goes off to the PIM unit? Is that simply a command that it drops into the API, or is there something more to it than that?
Oh, so there is an instruction buffer for each processing memory unit there, PCU, and the memory command only triggers the program counter inside processing memory unit. And also memory command supplies the address for the one of the operand for the actual operations. So memory command comes with whether it's read or write and the column address. That column address will supply the data to the processing memory unit, and another data will come from the internal register file.
Okay, and does software discover this automatically, or does it have to know about the existence of a PIN controller in advance?
So for that question, first we do have a device driver. So we designed the device driver for the GPU. Also there is a runtime, and also there is some compilers. So in this case, we don't need to change any application source code. And we have our own tool chain that can identify which regions of the code can be offloaded to the processing memory. And those will be, so let's say you are using matrix vector multiplication +2 routine, and it will get replaced, whatever the original plus library routine will get replaced with processing and memory enabled library. And those will be automatically handled by the runtime, stack, and the device drivers. So no change in the application code. And currently we are supporting the TensorFlow at the moment. We are trying to expand it for Python and other popular machine learning programming framework.
Excellent. And so if you have a lot of data and it spans multiple PIM units, how does the driver handle that? Or is that automatic, or does the programmer need to know about it somehow?
Currently, it's handled automatically by one of our runtime. So for big data structure, right, the data has to be spread across the memory. And not all the operations are done in the processing memory side, but some of the aggregations or reduction operations can be done the host side of GPU or CPU side.
Okay, very good. So jumping to the hardware aspect a little bit, with the performance or the power increase that you mentioned, or that Jin mentioned, the 5.4% power, is that on equivalent ISO capacity stacks, or is that measured some other way?
So in fact, we are consuming more power because of the processing in unit inside the DRAM, but that power consumption is actually offset by the reduced power consumption for transferring the data within DRAM. In fact, that power consumption is substantial. And in fact, if we could do some better job for the designing the buffer die, then we could actually lower the power consumption than the normal HBM. But at the moment, we try not to redesign the buffer chip, and we try to use the original HBM2 die. So that's why we have a slight increase. But if, let's say, we have a dedicated buffer die for this purpose, then actual power consumption will be lower than the standard HBM.
Okay, excellent. So there's another question that says, Slide 13 shows that the PIM bandwidth is 4x off-chip bandwidth, but you only gain 2x performance boost. How did that happen?
Actually, it's close to 3 times in most cases. And there are some inefficiencies. Let me put it that way. First of all, I mean, because we don't require any change inside the XPU side, the host processor side, yes, there are some inefficiencies. We have to maintain some memory ordering, and those overhead actually reduce the performance improvement. But in the future, some companies are working on improving the memory controller side and minimizing such overhead. And when we take that into account, we are getting almost 3.8x or 3.6x improvement for such applications.
Excellent. Well, that's great news. Well, thank you very much for the insightful answers to the questions, and give Jin a thank you for us as well. We've got lots of virtual applause on the channel. So again, thanks everybody for visiting this session. That's it for today. Please visit the posters, sponsors, and so on, and ask some more good questions at tomorrow's sessions. So, thanks, everybody.
Thank you. Thank you, everyone. Bye.